Hello there.
Hey.
Hi, hi.
Hello.
Hello. I wasn't sure I was going to make it today. I have my son and daughter-in-law and two grandchildren here visiting the whole week, so it's been very busy and crazy.
Yeah, I think you had mentioned last time also, like some people are visiting.
Yep. But I just finished the last, no, I have about 10 minutes left in the very last lecture. And boy, does it get complicated. Not complicated, but just so much
Definitely.
stuff.
Yeah, I just finished. I even like just 5 minutes before the meeting started, I finished the like last of the lectures.
Which is, yeah.
Yes,
I
like
can't.
it becomes pretty complicated.
So in theory, everything looks understandable. He presents it in a way that reminds me of Andrew Ng, the way he presents his materials as matrices operations with fairly simple, linear expressions. But then when you finally get into the homeworks or trying to use any tool, it gets hard very fast. So I can't wait till I guess we start doing lessons beyond just the trivial uh, things we were doing with um, the Network X. Can you combine Network X and PyTorch? Is that a thing?
No idea.
So I think because PyTorch, like the stuff you need to do with gradients and so on, you can't really do in Network X. I know that they have like for snap, they have the deep snap thing, which should in theory do some of those combinations.
I see. Oh, obviously we need the gradient. Definitely need the gradient right in the operation. It's the computational graph that is part of the PyTorch tensor. And I don't understand. I haven't tried yet, but I don't understand how that's going to work out to be applied into these graphs. Is that going to be the snap, you think?
So I think it's basically like if you look at PyTorch geometric, they basically turn the graph and the message passing thing into various tensors, and then once they've done that, then you can pass the gradients through them.
Oh, cool. Fascinating. Well, I can't wait. And I don't know, I guess future homeworks will have that.
So I know that like Collab 2, they're starting to have some of you're starting to implement a graph neural net.
Excellent.
With like PyTorch geometric and like some of your own code and stuff.
Okay. I haven't even looked at it, but that's getting ahead of myself. I just can't. It's always the way it is sometimes. Is like you can't believe the complexity. And then once you start tasting a little piece of the theory presented in a logical way, it's not so amazing. It's just somebody actually figured it out. So I like that about this technology. Yeah, I guess the tensors were a big revelation. Somebody working that out, which was what, 2004? When was the idea of combining everything together, the computation graph? TensorFlow. So did they do like PageRank? Was that all done manually in a sense? Early, at the beginning? It would have to be.
I doubt it. It's an iterative procedure, right? I mean, they might have thought through it manually, but I don't think the web was small enough even for the first time they used PageRank.
Yeah, I don't mean manually like on paper, but
Right.
but without an advanced technique for backward propagation.
Oh, they didn't need backward propagation. This
Oh,
is
you're
pure
right.
message passing.
Purely iterative
Right.
with results, and then just looping lots and lots of times. Okay,
Right.
that's true. That's true. Yeah.
It's
So I
like
guess
broadcast and aggregate, broadcast, aggregate. It's just, it's
yep.
like map reduce. So broadcast corresponds to map. Reduce
Accumulate.
yeah, right.
That makes sense. Why Hadoop and MapReduce was such, such a thing early on. It was the only thing, I guess, doing that
Right.
that compression, expansion, parallelization, and then reduction. Okay, that makes sense. Oh, okay. Well, looks like our population is thinning to a degree.
It could be, US audience is, is the July 4th weekend, so it's a long weekend for us.
Good point.
So yeah, so that might be the reason why some people are not here.
Yeah. Yeah. I'm gonna just review my slides real quick because I just finished, like we were talking about earlier, the slides on part 6, and it's hard to have questions if you think about it. If you're following the explanations, I mean, there's parts where I'm like, oh, that's interesting, or wow, who thought of that? But it doesn't. It's not that it's not understandable. Everything is understandable.
Yeah, it's like sort of like layers stacked together, but then I think homeworks will be tough because these layers have to be encoded.
Yeah, I'm sure it's going to get quite crazy because I just barely understand embeddings. I have to not think too hard about it, just take it for what it's worth. They're just representations and used later for nothing more than that same idea, representations, and then incorporated into that neighborhood aggregation.
So did he talk about, like, I don't remember, I could not figure out, like, did he talk about this, about size of embeddings? What is, like, is there any way to figure out, or some rule of thumb, something like that? Because he mentioned embedding, but he did not mention any way, like, how do we choose, maybe it might be in the next lesson, but till I think the 7th lecture, there was nothing on that. I was wondering, like, are all embedding sizes same? But then I realized that when it is multiplying with the weight vector, and as it is shared across all the nodes, so it has to be it has to be on the same size, the vector size of the embeddings.
Good
Not
point.
necessarily, right? It is dependent on your problem, how much representation capacity you need for your problem. I mean, if you were doing a one-hot encoding, like the first PyTorch example, in the, I think Collab 1, they had that, right? So if you're doing like that, then yes, I mean, it's a one-hot encoding, and you say, okay, I am the 5th node, and therefore, it's like, and out of 34, so it's like 0, 0, 0, and then 5th position is 1, everything else is 0, right? But that's typically not, it conveys no meaning, basically, right?
Mm-hmm. No, I'm talking about, sorry, I should have specified, I'm talking about the GCN or maybe GraphSage, which where it starts with putting that into the graphical networks. So I'm wondering about those embeddings.
I see, okay.
So initially I was thinking, because like each node is taking information from its neighbors as well as its own information, I thought that, like, yeah, the size will be different, because maybe they're one of the ways we have that is we can concatenate all that information. But then when he talks about that weights are being shared across different nodes, then there is aggregation function. I think what I understood there is like that implies that the size of the embeddings in terms of like how long these vectors are or tensors are, they are of the same shape, the same size.
Okay.
But yeah, not directly said anywhere, but that's,
right.
I think that is sort of implied.
for each node. The embedding size, of course, is the same, right? And just for the math to work out, since the weight matrix is the same across all nodes,
Right.
that does imply some uniformity or consistency, but it doesn't know nothing about scale. And maybe that's Sujit's comment about it has to be enough to express what it is you're trying to express, because that's where the expression is, right? It's not in the weight matrix. That's in the control or in the behavior mechanics or something. It's expressed in the embeddings, which represents the feature space. Yeah. But what's typical? I mean, so for example, LinkedIn or Facebook, they don't try to do problems across the entire network. They choose a little piece of it, I presume, that's meaningful to the problem, which might be predicting my next job. It wouldn't make sense to have things way too much beyond me. Maybe a little bit for modeling purposes, but is that the idea?
Yeah, I think you're. I'm on this. I agree with you. So, in one of the things he talks about is that the depth of the graphical networks is different from what we have in CNN. So the depth sort of tells you like how many hops you are taking, you're taking the data from. So in if I in like in a very big, even in a very big network, we have something like for humans we have this 6 degrees of separation.
Right.
So if I say maybe with like graphical new network of like depth 6 or 7, we can cover the whole population of it. That's what I
see.
think might be implication there. Now, so yeah, he talks about that there is this smoothing issue that if your hop distance is very big, like if you're getting information from everyone, then all the nodes become very similar. So that's why you have to figure out like how deep you want to go, and you have to make sure that you take information from only relevant part. And based on what I understand from that is that based on the depth of the network, we can define what is the what was the word he used? I mean the region from where we are getting the information. This is one specific word he was using. I'm forgetting that.
Diameter?
No,
diameter will be the entire graph, right? Yeah.
No, it's also used in CNN also, like basically to understand in what is the area from where you are getting the information. What is your scope of
your region or locality or neighborhood?
something like that, but
yeah, I see.
I'm not able to remember that specific term.
Right. So the fact
receptive field, yeah, receptive field. You talked about
Receptive field. Okay. All right. Yeah.
Specificity?
No, receptive field. That's
receptive field.
Yeah.
Receptive. Okay, that makes sense. Receptivity.
Yeah.
That's basically the signal coming from some distant node.
No, I think not receptivity, receptive field. Basically looking at what is the total size of your total number of total connections from where you are getting the information.
How
so
much
basically,
can you see? Yeah.
How much can I see? Yeah.
Okay, that makes sense.
So if you increase your receptive fields to such extent that you are getting information from everyone, then all the nodes degenerate to a single state. They're very similar. They become very similar. So that has to be taken into account. But then he also mentioned that inside the before aggregation function, how do you aggregate the data? You can have a simple functions, or you can have even some sort of a neural network there, deep neural network for the whole aggregation function itself. So it can be you can increase your processing power, I would say, through that, like how much patterns you are able to absorb from your neighboring nodes based on the your definition of your aggregation function. So that way we can increase this.
Does that definition depend on something other than the geometry? or doesn't
definition of what?
doesn't the geometry, the connections define the network that you have? You know, he said that every
Maybe.
node is going to be its own computation graph because it's unique. But
Yeah. So
how do you alter
so,
the complexity?
Different weights, I think, just like CNN filters, right? So how they are combined, or to what extent each node contributes to the combination.
Is that unique per node?
yeah, no, yeah, somewhat on the same lines. We have attention weights. So it talks about the attention weights. Has someone downloaded the slides? Because I don't know whether this website is not opening. We can just open the slides and we can talk to what with those slides.
Yeah. I have a YouTube video. I'm watching the YouTube. I don't have the slides.
Okay. So I don't know. So if someone has slides, you can share on the desktop so that we can directly talk about those things. Yeah. So yeah, coming to that point. So he talks about the attention part, attention values. So if I have a node A which is getting contribution from 3 other nodes, I can have different attention values called alpha. So I have A and it is getting information from maybe XYZ. So I can define 3 alphas there. So alpha AZ, alpha AX, AY, and AZ. And based on those weights, I can learn those weights based on what my loss function is and how much I'm able to perform. And using that, we can have some sort of attention values for each node. We can have some sort of a attention mechanism which decides like which nodes in neighborhood has to be given how much weight.
Okay, I didn't get that far. I don't think I got to the point where the weight matrix was shared across all.
So I think it's after that. So if you go further down on the slides, so it talks about this attention part.
Yeah, this is 6.3, right?
Oh, sorry. Okay. Yeah, I think it's before that only.
Oh, was this in the last 10 minutes of the?
Yes, I think yeah. So for the aggregated, taking the weighted, can we do better? Yes, this is what
I missed it. I missed this. I haven't got here yet. I had 10 minutes left.
Yeah, so I think 63rd slide he starts talking about that. Second 62, 63. Oh no, further down. I think yeah. Sorry. So this was just about getting information from the neighbors. Now he's adding information of the node of the previous state to himself.
I got that.
Then he goes further.
It's unique per node. Wow, that's powerful.
Yeah, like the number of layers this lecture has added compared to the previous lecture is ginormous. I don't know, like, are we going to have other concepts also, or the next all slides lectures will be all about the implementation of whatever
thrown to good question. It can't get more. It can't go much further out than this, but of course, it can, because for every loss function, every time you mention loss function, you can go down 5 or 7 different paths of just loss functions.
Yeah, but I was wondering, like, so the attention-based graphical networks were proposed in 2017. So I guess there would have been a lot of improvement since then, and I guess we are going to see a lot more. But I guess this is the basic structure. If you go further on slide 65, 60 somewhere, he starts talking about those alphas, which I was talking about. So the graph information.
Got that. Oh, that's the recap. Yeah. Okay, I must have missed the attention. So is that also, let's see, I'm trying to think of what's tracked, through the process of iteration of backpropagate. You have to track things. And of course, the weight matrix is being tracked and updated. So are things about every node. Yes. And one of those things is this attention function. That might be fairly simple, in essence, because the small graph that's represented for every node is actually quite, it's only, you know, a handful of neighbors, right? And maybe one degree past that.
Yeah.
Yeah.
So like I guess yeah, 1 or 2 degrees would be more than enough in like a lot of the cases. The 2
Yeah.
degrees give you a lot, a very big receptive field. It's like what my neighbors are also looking
Right.
at
Right.
with the first degree connections. That is pretty big. If I know 10 people, my and each of them 10 people know like 10 more, so my receptive field becomes 100. So that's a pretty big number.
And how many? What's the features? You know, a given feature set of features for these nodes. 10, 8 or 10, 12. You know, things you're trying to measure about each node.
Yeah, he didn't talk about that, but yeah, that's what I was wondering. Like, what is the size of encoding? How much data it has, and how do we
Right.
define that?
Like
So he did not talk about that much yet.
job type, years in service, age. You know, those things that you're actually having to, the data about each node, the features.
Yeah, there'll be. I guess there will be 2 type of data there. One will be dynamic, which will be changing over time, and another we can have for individuals we can define static as well as dynamic. So and we can concatenate them, something like that.
I see. That's pretty interesting. I can't wait to get into it, little by little, little by little.
And so if you see connections here in the graph stage thing, there is each connection from the red to another, all other nodes. For this red, all other nodes will be contributing data as well as itself. So that's what the violet arrow represents. It has like 2 arrows, but it should be 1 only from him to itself.
Yeah.
And now you can give each a different weight there. That will be a weight, and that will tell you like how much attention you are giving to which neighbor. So that's how you define the attention part there. You learn that while backpropagation. That is a theory I have understood just half an hour before.
Okay.
So, so that's pretty incomplete, and I don't know how to do it.
You learn that weight for every node.
Correct.
Wow.
No, I don't think so. I think like the message passing thing, you have a set way of doing the aggregations, and then the weight matrix is the same for, you learn one matrix and you use it across all the nodes.
Weight matrix is same for everyone, but you then have a like attention. I would say let you call it alpha, some scalar. So that will be multiplied to the weight matrix for each node. So the weight matrix will be shared across every node, but for each node you'll have specific alpha. So if you go further down the like slides, there's one equation which talks about it. So,
I think it's the next lecture, isn't it?
it could be maybe 7.3 or something.
Oh, I didn't get to 7 yet. I see. This week was only 5, 6. So
yeah,
so okay, good. Just want to make sure I'm clear. Okay. Oh yeah, there's an entire factor per VU pair.
Yeah, per direction.
Yeah.
So it could be other way around for I'm not sure, but I think it would be other round way for other nodes.
But it's
so
a scale. It's a scalar. Yeah.
It will be a scalar for one edge. Let me think.
Oh, a vector. Well.
Yeah, it will be a vector.
It's one value per node pair.
Okay. Wow, that's power. That sounds powerful. And learned per node. Sure, why not? I mean, every node is we're iterating through every node, every epoch. So sure, that's learned.
Yeah, so maybe you can think of like this like that. Like the way I understood is like if I'm looking at maybe LinkedIn, so so this algorithm will learn like which people I more interact with or which posts are keep on liking, and it will keep on giving those weights like a higher like
Right.
attention value to them. So I'll be seeing more of them in my feed.
But
So,
only to accomplish during training, only to accomplish the objective, whatever the objective is.
yeah.
I see. It picks up this. In
So
addition,
it can be something like that. Like I'm just thinking while talking. So if it maybe something like it predicts which all posts I'll be liking and which all posts I'll be interacting with, and then it checks how close it was. And if it is not close, then it will go back and check, modify those attention values.
while the weight matrix, the big W, is really kind of getting the behavior of the entire graph in
True.
order in some bigger, not, it's not really big or small, but it's something different, something less tuned to the nodes, but more behavioral about the graph, maybe. And I was kind of wondering about applying the entire weight matrix to similarly to every node. That does sound like you're missing some very minute stuff, but then that's picked up maybe in this attention.
Okay, so there is one place where where your this matrix, what is it called, you define connections. Forgetting the names. I keep on forgetting jargons. So okay, what did we start with that matrix where we have columns and rows as different nodes, and whenever there is a connection, there is value 1.
Aggregation.
Yeah, so you multiply that to the W so that you only take weights of those ones whom you are directly connected with. So you are not taking all the weights into account, but that otherwise it will become everything. Others, whenever it is 0, it will become 0, the weight effectively.
Mm-hmm. Right. Yeah. Okay. Interesting. Well, okay. We are moving forward, moving fast.
Yeah, this lesson was pretty daunting.
Yeah.
Inward.
Oh. I'm gonna look at the homework scoping. When is that coming up next? So looks like Colab 2 is out there, but not due for we should be starting it. Is that right?
I mean, on the schedule, the initial idea is that it's collab 1 and lectures 6 and 7 this week.
Right. Okay. So we should be kind of done after today. We should have Colab 1 behind us in the past.
Good.
And I think we covered a fair amount of it last week and the week before even.
Yeah.
Yeah, I did not go back in and finish the homework 1 or homework 0, actually, I'm sorry. So I don't have much to add on Colab 1 or homework 0.
Well, I think kind of homework 1 is more practice on the networking stuff. So if you start working on homework 1, you'll probably also help you get more familiar with the network constructions and etc.
Right. Well, that's definitely on my, that's the agenda for this coming week, of course, is to nibble at homework 1, maybe begin on Colab 2. And, oh, I see. 7 was actually this week, wasn't it? Oh, I did not do that. I thought it was just 5 and 6. Ooh, I am behind. Yeah, good question. Is 8 and 9? How much more broad can this technology go at this level?
Yeah, just now I was able to open this. So he starts talking about design space, then theory of graph neural networks, maybe goes more into mathematical theory, what is happening there. And then he starts about knowledge graph embeddings, reasoning, applications. So,
Okay, good.
I think I guess
no.
even if you do half of this course, that we are in a pretty good position to do a lot of stuff.
Sure. I do like to get through the homeworks. I like it's where the rubber hits the road. And
True.
just like we actually went through the collab last week before, it was very helpful to me.
Helpful, totally.
Yeah, so I expect to continue that degree right through the rest, but I can only do so much per week, and so far it's pretty good. Things open up this week for me with a little more time available. I think for the rest of right through the summer.
So I think some of the key concepts of graph neural nets is actually in these two lectures, like distant message passing and attention, and then I started watching 8, and that's more kind of around like the practicalities of training graph neural nets, like what does the training, for example, how do you define train and test sets, like loss functions, etc. So there's less of this sort of stuff that you need to understand, but more about like, okay, I have this problem, I formulated it as a graph now, how do I train a net on it, sort of thing.
Great. That sounds great. The real nitty-gritty of implementing the theory, which itself looks fairly reasonable. It looks reasonable. It's interesting and reasonable, which is always good. So I wonder if David Collier is going to jump back on. Maybe not. I couldn't quite get the gist of.
Hey, I'm actually listening in.
Oh, hey, man. How are you?
I'm good.
Good.
Sorry, I personally haven't had any time to work on this stuff, so
I know. It's I think it's going to be overwhelming. It seems overwhelming, actually, unless it was like almost a primary function. This is the only academic thing I am doing.
Right.
For the next 12 weeks. I've committed to that. You can only do so much academic.
Right.
Can you imagine doing this with 3 other classes just like this? I can't.
Yeah.
Full-time student. That's what you're expected to do, I guess.
Still, I thought my classes were hard in engineering school.
The only study I've ever done is going to art college, and it was throwing paint at walls, so it was a lot different than this.
Yep. Well, just dig in when you can and observe, but wow, this stuff is hard for me.
So the theory that's here on, I'm just looking through the document 6, which I guess you guys might have reviewed already, where it starts going into the graph weighting, where it's initializing the node and getting a final calculation for each node, I guess around like slide 21. Is that something that we're able to walk through with an algorithm and kind of like in a debugger or something like that? Yeah. Well, I think I'm looking at a different slide than you. I'm looking at the one from a different deck. I'm looking at the one actually off the latest version, I guess, off the. Oh no, I'm looking at 2019. Right, you're looking at 2020, I guess. Maybe I bookmarked 2019 because I had homework assignments or something. Well, they basically have, I don't know if it's in this deck as well, but they have kind of screenshots of, well, they just have diagrams of the network, and it shows them the math kind of iteratively going through the nodes and coming up with a value for each node. Is that something that I think, Wendy, you mentioned the next version or the next lecture is talking about implementing your graph library, maybe PyTorch graph or whatever it is, but you can't kind of step through. And is there a simpler way to just kind of like trace through the code and see these weights getting applied as you iteratively call a function on the network?
So that is done in Collab 1. So I think we were discussing that last time. So this is basically the page rank algorithm. I think you are talking about.
Right, right.
Yeah, so that is mentioned. That is there in Colab 1, and there you have to specify the weights, and so it will ask you to ask you what is the for that specific node 0, I guess. What is the weight after one iteration? But you can use there is one network X in the network X also. There is one function defined which will do this for you. You don't
Right.
need to write the code.
Got it. And you guys are using the 2020 version or the 2021 version of the class in the end? I thought there was some discussion about using an old one because the latest ones didn't have materials or something like that. But
That's only for the homeworks, but
For
like
homework,
the stuff is the 21. So
yeah, videos are getting uploaded to 2021 version. So for videos and slides, we are using the latest version, but and also for collabs. For homework, we are using the 2019 version.
Got it. Okay, thanks.
Sometimes stepping through these things is actually kind of difficult, but a few times it was like, in this case, same way with PageRank, it actually does define like one step, and you have to manually kind of code the contribution from the other pieces as like what's going to happen on the very first step, and then you can do that. It's almost like it's not even a toy. It's just a very almost laughingly simple representation, but you just get the idea of what it's doing. And I remember doing this for other deep learning neural networks where you actually code the back propagation once, but boy, it's got so much detail to it. You got to make sure that everything matches up, especially if you're using vectors.
Right.
And then you kind of let the system, you assume it's doing it right, and then you just check some things after every epoch, or even every batch. You can, of course, PyTorch has the ability, as you write your algorithms, to output data at every loop if you wanted to, or every 100 loops.
Right.
Yeah.
Interesting. Yeah, it looks like the class website is down right now, ironically, unless it's my connection.
No, I think it was not working for me also. I think it's just open. I'm not refreshing the page now. It wasn't working for me too.
Stanford was down. Ouch.
Interesting. So you were using a collab last week. Was that the one that Wendy did, or is that's another, the course collab?
just a course collab. Like we're talking about collab 1 from 2021.
Okay. Yeah, I can't get to that right now.
Yeah, and I think the at least my revelation after somebody helped me understand how to make the PageRank function in Network X only go through one iteration. There's actually a parameter for the number of iterations, and I put it in as 1, and it basically failed, blew up because it said it didn't converge. That's because the default threshold for convergence is like 0.001 or even smaller. If you make that very large, then it will be okay with just one iteration. Little key there. And I think it was TOL. That's the threshold tolerance that you can make very large, and it will spit out the answer after one iteration, which should match.
One iteration means one traversal of the whole graph, or?
Well, in that case, it's the PageRank with respect to, I guess, that one node.
Right.
It's the actual rank number.
Right.
Ranking. It was like 12.7, and it converges it to like 13, something very close to 12. But even getting that same number after one iteration manually compared to the one from Network X was satisfying in that it looks like we got, you understand how to do it, and it's fairly simple.
Yeah. Does the way the PageRank algorithm works, do they just pick a start node at random and kind of continue walking through the graph, or are they doing like, is there some method for doing like simultaneous calculations? I mean, if you left all of the magic of the PyTorch library behind, could you effectively write your own thing that just goes node by node and does some calculation based on the previous node? But you never really have I mean, you don't know what the value is when you start the whole calculation, right? You don't know what the influence of the previous ones is. So you just pick a number and then just keep iterating until things kind of even out.
Yeah,
Yeah.
as I understand it, you just basically everybody starts at the same value, and at each iteration you keep the value of what you know about the nodes constant. So like say I have 5 nodes and I calculate them in a dumb way one by one, then then kind of like in the aggregation, I'm not considering the current state of the node. So for example, if I've updated 1, 2, and 3, I don't use the updated value. I just use the original value when I'm updating 4. And then so they're all updated together.
So you can assume it like this, like you can say it like this, that instead of one person transversing all the things, you can have like as many nodes are there, you can have as many people on those nodes, and then you give them that you take one step based on like whatever the probability you have initialized with. So then based on that, you get these 5 outputs there, like whatever outputs you get after one iteration. So that is equivalent to one person going through maybe through all the.
That updates all the nodes. That one step updates all the nodes, and the next step takes the new information from all the nodes. Yeah, and that's
so. If you, yeah, so
I don't think it matters where you start.
It's using some kind of basically a matrix calculation to update all the nodes in one calculation. There isn't a concept of like going from node to node, like a kind of traveling web analyzer salesman kind of thing.
Right.
And figuring it out.
That's a good question. And I guess that feels right, that it's assessing the page rank on every node in the network after one iteration. Is that correct? Anyone?
So what I understand is that one iteration is about updating the weights once for all the nodes. But if you think that in terms of one person visiting different nodes, that is different. So that is not one person just moving to another node. It's like if that person starts from each node, so what will be his next position be? So you put one person on each node, and then you track like where he ended up, and then you update the weights. So I think that is the way we can understand that. It's not one person. There as many nodes are there, as many person we take, and then we update the nodes parallelly. So because the updation of the nodes is not exactly dependent on each other.
Right.
No, it is dependent, but when the final output is not dependent on like in what sequence they are updated, maybe.
That's
because,
right. Yeah, go ahead. Sorry.
Yeah. So because as you know, like if it's a Markov equation, and whenever the Markov equation converges, after the conversion, it doesn't matter like how many times you do it.
Exactly.
It keeps that state.
Yeah. Keep going. Sorry.
Yeah. So I think taking too much time there.
No.
So instead of looking at one person moving through all the nodes and then updating, we can do that independently, because in the end, when it converges, it will be like that person, whoever is at node X, will remain at node X only. So that will not depend on like the whole idea that where the person will go to. That I mean, the graph itself becomes stable in terms of weights.
The choice that the person, if you're metaphorically, there's a person moving through, the choice of where that person goes is random, or are you following a path to?
That's the point. I think the concept of one person, that's only the setup of the theory.
Right.
is to imagine a person, but
Yeah.
he's actually operating on a probability space that you're trying to calculate.
Right.
And the probability space is being calculated after all the iterations.
Right. But the probability is only, there's only a value for the nodes connecting to the one that you're on right now. There may be a value from the previous iteration of the outgoing nodes, but if you're on node 3, the algorithm allows you to calculate the weight of all the inbound connections, but it doesn't really help you make a decision about the outbound connection. I think is how it worked when I read through it, but I'm not sure if I'm misreading that.
But your outbound values are the ones that you give to your connections.
But how do you, just from the previous iteration, or are they the randomly assign them at the 0 iteration? Because there's value of the node and a value of a connection.
Yeah, you randomly assign at the 0 iteration. You start with a random weight, and maybe it's, you can understand it other way around. Is like you just look at from the perspective of that node. If it has values, different probability of values inbound connections with different probabilities, you can and if that node is trying to register from where the person might be coming, so if the probability is divided, like if there are 3 inbound edges for that node, and it is like let's assume the probabilities are 0.6, 0.3 and 0.1, so that node would expect like in its stable state, if that let's assume that in the stable state is 0.6, 0.1 and 0.3. So in a stable state, that node would expect that the 60% of the time the person will be coming from that node which has 60%, like 0.6 probability with that incoming edge. But okay, so that is the final state. But if we start with some random state where those inbound edges have different weights rather than compared to the stable state, and we starting with random state, then the way we are updating this, that maybe I've given the equal probabilities to all 3 nodes, 0.33, 0.33, 0.33, no, not nodes, the edges, incoming edges. But you can update that in update them regularly, because whenever if the node starts counting how many times I see, maybe out of it, the person moved through the network maybe 1,000 times, so it can update the nodes based on this, that how many times compared to my prior probability value, I could see the person coming from maybe edge A, edge B and edge C. So I cannot basically keep on updating those values till they stop updating. I mean, the actual number of incoming times is in correspondence to whatever the probability I have updated them to. So you can think that way. So each iteration is that updating that.
Right, but in the graph data, it encodes the knowledge of the kind of authority of incoming nodes. But let's say you've got 3 coming in, like your example, but you've got 2 going out. Does it just decide at random? Does the algorithm work on a kind of single person moving around the graph concept, in which case it has to make a decision at every iteration about where it's going to move next? And does it do that randomly, or is there some kind of encoding of the value of outbound nodes or outbound edges, or just inbound edges?
Yeah. So for outbound edges, I'm giving equal probability. I'm basically dividing all my importance. Let me call that importance there, into 2 parts and giving them to outbounding, like 0.5 probability. But now think of the node which is on the outbound side of me. Like I'm on a node and I have some other node X which is at outbound side of me. Now it might have connections from 2 other nodes also. But then if my importance is low, the probability that the person will be coming from me to that person, that node, will be lower. So it could be, for me, the probability of outgoing is 0.5, but for him, the person coming from me to that X node is lower because I have lower importance. So that is the whole idea of giving the
Yeah.
importance.
But that sounds like the algorithm would have to have kind of look ahead knowledge of where it's going, not just like a historical knowledge of the path that it had traced so far, which seems very, very complicated, because where do you put the cutoff point?
Like the graph is already fixed. There's
Right.
like the connections are fixed. You're just changing the every update.
Right. So you add the weight to the edges on the update, and you have look ahead knowledge of the connected outbound graphs to use to decide. But I wasn't even sure if it even is implemented as a single element, basically walking through the network, or whether it is somehow that all of the adjacency matrix is encoded, and in one huge mathematical function, you're able to kind of multiply two matrices together to get the next iteration of the values, which would seem to not scale too well, because if you're doing everything, if you have to do everything in the node at once, sorry, everything in the network at once, I'm not quite sure how you can parallelize that, but maybe that's separate.
But as I say, it's kind of like you may, because you know the starting state, then like you can update them all together, you can update them one by one, it doesn't matter. You use whatever you know the original starting state is, and you update all the nodes in kind of like.
That is a good observation, though. Is it done in a big outbound wave, percolating outwards all the way to the end?
No, I think it's not like you can. I think you can think of it as they're all updated together. I mean,
you can update them all together.
Whether they actually do it in the implementation or whether they use an iterator, you can think it doesn't really matter in terms of the concept. The concept is that you update it all together.
Good point.
But in theory, any node could be connected to any other node in that matrix. So I don't.
No, you can't, because the connection is already determined. You're not changing the network.
Right.
Yeah, you're not changing the network.
Right.
So yeah, you can do that in a like very parallel way, in a matrix way also. So you can have this if you have weight matrix, that is importance matrix of. So let me think that I'm just assuming that I'm just thinking how it can be done. So you have this vector of all the weights of all the nodes. Now you have degrees of. I mean, you can have a degree matrix where you can take the inverse of the degree matrix. It can be a diagonal matrix. So for each node, that point will be 1 by number of degrees of that node. You can just multiply with that, and then on diagonals you will have so each vector will have its weight divided by what is its outbound degree. So you can have this outbound degree matrix there, and then you can multiply it with the adjacency matrix. That will give you a next iteration by updating all the weights at a single step, because the inbound so update for the node is based on whatever from what are the inbound connections, and that has to be weighed down by the importance of the neighboring nodes. So that will take care of this whole probability thing, that the one which has lower importance will get less probability in terms of my inbound thing, even though on outbound thing I can assume every outbound edge has a equal probability. So that way I don't need to worry about the outbound thing. I can focus more on inbound inbound edge weighed down by the importance of the neighbors, and then will take care of everything.
Right. But assuming that kind of outbound even weighting, that more seems going back to an approach where you're walking through the graph, and at each iteration you can only choose one way to go. You can only choose one next node. So you move to that one, and then you calculate everything, and then you move to a random one of its connections and calculate everything. Whereas if you were doing everything in this kind of like wave across the matrix, you wouldn't need to make a decision about where you're going to locate your theoretical person, because everything would be, you'd be applying, you know, one kind of big slice of math against an existing version of the matrix to get you a new result. It doesn't really have the concept of going through like kind of imperative code, like a glorified for loop going through every node. It's just like whoosh, we do the whole thing at once. So I'm not quite sure how to resolve those two different ways of thinking about the implementation and how it's generally actually done. So,
I think if you look at the notes, like
right.
from a few lecture 4, maybe it's not there. I think if I remember correctly, that's what they talk about when they talk about power iteration.
Right. Okay.
Yeah, I just looked at the source code on Network X PageRank, and there are some references at the bottom. From 1999, which might shed light, but actually the code itself does not really indicate how it works, which is kind of weird. I thought there would at least be some indication of what exactly your question.
Right.
Power iteration, you know, it might be worth looking at the source code.
Yeah.
Maybe not. It's not that can go both ways.
And that code for Network X, I haven't actually dug into it, but it's not kind of delegating to like a C library or anything for that kind of calculation. There's actually just Python code you can look at.
Yeah, it doesn't seem to be. It does
Okay.
say it uses eigenvector, some library for eigen NumPy. You know, it just uses more Python somewhere.
Yeah.
I can.
So in fact, instead of using the way the Colab does, a better way would be to use the eigenvectors. Like it's a Markov equation, so we can use the eigenvectors to know like what will be the n+1 states based on it. So
Yeah, you're pushing my comfort with math pretty quick. I'll be quite honest. Dot products, I understand. Eigenvectors, still a little hazy. Always.
Well, eigenvectors is basically you multiply a matrix by something and it returns the matrix itself with a constant.
Okay.
So I think Gilbert Strang touches that in one of his lectures. I can't find out now, but
yeah, he does cover it. I do remember at the very beginning, it was pretty succinct how that is, why that is so valuable. But it's still, I'm sure there's a 1-hour lesson on some website on eigenvectors that I should do to fully understand it.
I think I need to look at, I think there's a guy called C. Brown or something like that on YouTube. That's pretty good.
2 red, 1 blue, or whatever that. I love that site. The guy that explains things so perfectly.
Yeah, C blue, 1 brown.
Yes.
1 brown. Yes.
Yeah.
So
there's like he has got a playlist on matrices, and it's actually it's quite eye-opening because he kind of like explained it in terms of like actual geometric understanding.
Okay. Very good idea. Very good idea. Thank you. Yeah, my whole understanding of Bitcoin is based on that one video that he has. which is just incredibly detailed, but great the way it works out. It's just useful.
Have you guys explored much of the NetworkX APIs in terms of different ways that it can manipulate the graphs? For my purposes, where I was trying to get rid of like loops and stuff, I noticed there are functions to kind of remove loops and things like that. It does some nice stuff like that. One thing I did have a tiny bit of time to do this week was get Neo4j installed, and I was looking at for the actual projects I'm working on, I was just looking at using Cypher, which is their kind of query language, like SQL, basically for graph queries. You can do things like find shortest path. You can give it like a couple of named nodes, and then I don't know if you guys have used it, but the query language is kind of like ASCII art. Like you use like a couple of round brackets to indicate nodes, and you use dashes and arrow, and a dash and a greater than is an arrow, and you use that to indicate a directed connection. So you kind of have a named node of this, and it's like, find me the shortest route between these two named nodes or pages, whatever. I was just wondering if there's anything similar in NetworkX for that kind of just more like procedural manipulation or exploration of graphs.
I have no experience in using NetworkX other than what we've been doing here.
Right.
And Neo4j, somebody at work is actually looking at it a little bit. It seems useful for actual implementations, but I don't know how the two mix at all. I'm sure there is a world where Neo4j.
Well, presumably they're using similar mathematical theory, like under the covers, to implement Cypher.
Sure.
But I'm wondering how it's a different way of looking at the APIs. Like in Cypher, you can select subgraphs. You can, detach one group from another group and get like the number of, get counts on the number of nodes and all of those kind of things. But it's a completely different way of expressing what you want than you would do it in Python, because you literally, you just put a bunch of Cypher in quotes and pass it to your database driver.
I mean, like NetworkX has more or less those same things. It's just that you're calling a Python function rather than Cypher.
Yeah.
I think kind of the only the big difference obviously is that NetworkX runs in memory, and there's limitations to how big a data set you can dump into it.
Yeah.
And like obviously there are various optimizations and stuff that, like for example, if you have too large a graph, then NetworkX is can be quite slow, so on and so forth. But I think kind of like graph databases will obviously also have their own issues around like how easy it is to kind of say, for example, implement like kind of like you have to install extra stuff, whatever.
Yeah, I was just doing a graph with like 5,000 elements and quickly hit like very, very long queries, just looking for paths between things. So I think it is quite easy to shoot yourself in the foot. But yeah, that's the Stanford library that they were using for the graph exploration. I found that a real pain to use. It was always coming back with like wrong type or various things like that. NetworkX looks a lot more kind of user-friendly and rounded out as an API. I don't know if anyone had a similar feeling on that, but maybe the Stanford one is more performant. It looks like basically like a C++, very thin wrapping around their C++ library.
I have no experience there. Yeah, I'm kind of balancing certain aspects of digging into any of this tooling. So I'm still at an academic high level.
Right.
You're a very practical implement. You have a a big desire to get some implementation out of it.
Yeah, yeah. But I guess it's just how different people learn. I find it very hard to learn in the abstract. I learn if I have like something I need to get done. So yeah, but yeah, it's interesting just poking around, comparing those two different libraries in order to solve the problems.
Yeah. To do something fairly simple, you might say, shortest path, and then
Right.
comparing one to the other step by step. That's always a good exercise.
Yeah.
So, okay, I'm gonna take off. I don't know if other people want to continue, but I have some folks kind of waiting for me.
Yeah, I'll take off too.
All right, as well. Hopefully Stanford will be back online by next week.
Yeah, we'll do our best to keep the topics fresher in Slack, but it's hard.
Yeah.
It's hard just to keep up with the material enough to much less put stuff,
So are you guys working through your own separate collabs? I didn't see that much chat in Slack this week, but
generally, I think that's kind of the strategy, is to everyone kind of do. And then if you have particular questions, maybe you kind of bounce them up a little bit, try to represent them in a way, versus just kind of everybody sharing the same code. It gets a little funky.
Yeah, I mean, I'm behind you guys. So actually, I found Wendy's notebook very helpful to figure out a couple of the things on the statistics stuff that I hadn't really thought of. So I'm just was kind of slipstreaming on that, but I didn't do it in a notebook. I just did it in raw Python files because I find it easier to step through in a debugger and find out what's going on if I need to.
Indeed, there is a debugger for Jupyter. I forget what it's called.
It's IPDB, I think.
PDB, that which has helped me in the past.
PDB?
PDB, yeah.
PDB is like the Python kind of basically command line debugger that you can always drop down to if you want. Yeah.
But it does expose stuff willingly, which is nice. Yeah.
Yeah. So basically someone's put a Jupyter component that allows you to kind of interactively, I mean, I would say Jupyter in a way, the whole thing's basically a debugger in many ways. It's just
it is indeed.
Here's your state,
Yes.
We're not going to modify anything, and we're going to print out the state as a nice graphic. It's kind of like the world's best debugger in many ways, I guess. But
it seems like it. Yeah. I'm not sure if Colab goes to the same degree. Can you run PDB in Colab? Sure. Well, I don't know.
I think Colab is just basically a notebook in a Dockerized environment thing.
Probably. With some.
You should be able to do the same stuff with it, like debuggers and stuff. I mean, for me, I've always when I need to debug a function, I always just put it in like PyCharm, because I just find it a lot more intuitive.
Yeah, everybody has their comfortable place.
Yeah, and their pet IDEs and whatnot.
Yeah, PyCharm is a big behemoth of a thing for sure. But
I guess you can just run a notebook right inside PyCharm, same as Visual Code, right?
Yeah, you can. True.
I'd be interested. God knows what GitHub's Copilot is going to do for people's homework. You just type in the comments on the problem name, and boom, there's your answer.
It's also true that you can't really trust it completely, right? You always have to actually look over it, make sure that it understands.
Kind of have an idea. I think Dave was mentioning you knew the answer from one version was 12.7 and you managed to reproduce it with 13. So yeah, if your Copilot code comes out, unless you look at the code and the code's return 13.
Exactly, equals, which you hope it might in some cases. But then this is the same things they said about graphing calculators back in the 80s.
Right. Yeah.
So here we are.
I mean, you can look at the code that's generated and try and learn for it, or you can not and just try and apply it
Yep.
apply the results of it, and that, you know, there's a use case for people doing both types of stuff.
No question about that. Yeah, it is fascinating though, the whole utility of code generation.
Yeah.
Fascinating.
Well, I mean,
but I feel like it's like every time you'll have to look at the code, it's like debugging someone else's code. And for many of the cases, I would rather write a fresh code than debug any other person.
so you never look on Stack Overflow then?
I do, but then
like,
yeah, I have to.
But look on Stack Overflow, you also definitely review what they're writing. Or at least I don't know about you. I never read copy and paste it and not think about why I copy and paste it.
Yeah. I mean, I hate it when people just put code without any explanation. It's like the whole point of Stack Overflow is to understand and to get the answer to your question, not just, well, unless it's some ugly regex and you just can't be bothered to understand what it's doing. You just want to like, how do I get a, you know, Python regex for a URL or whatever.
It's very rare also that your specific condition matches that person's specific condition.
Yeah.
Yeah, at most you can get some chunk of code, but yeah, not the whole.
Right. Like, oh, here's a new way here's an interesting way to use NumPy, or oh, I didn't know I could do a slice that way.
But I think it also is a problem of like the languages we're using have not really got a lot better, but the problems that people are doing are getting more complicated. So there's a lot of boilerplate that's involved. I don't know if you've written like React front-end code, but like, you know, to store something in Redux, you have to like create 5 different files and do all these different things. So in some ways, Copilot is like a short circuit for the problems that we've developed, that we haven't developed higher level solutions in languages to solve. So rather than cutting out boilerplate, it's kind of like a boilerplate generator in a lot of ways, which it seems like we should have a better solution to that stuff than by now. But
yeah, I've heard that same thing about React, and all it is framework on framework on framework. It's not really solving the essence of the problem.
Yeah, I mean,
I think sometimes it's quite hard because like there are certain times when you do want some boilerplate to kind of make sure you maintain a contract between different layers in the software architecture.
Yeah.
So you can't really say like if it's, so there's like, okay, so maybe you want something really simple and you just want it in one file. But if you look at the whole picture, if you need to build something more complicated, then maybe that one file is just going to cost you a lot of headaches down the line. So there is sometimes logic for having boilerplate.
Of course, yeah. Frameworks are there for a reason, but it seems like we always visit many of the same problems over and over, like David was saying.
Yeah, but maybe the Copilot is like a way for you become like a boilerplate architect. You just kind of write the first line of every piece of boilerplate, and it's filling in the rest of it in the background. If you could just like collapse those functions so you don't need to actually look at all that stuff, and you're just looking at it at a high level code, but kind of delegating to your buddy. I'd be really interested if you could do like Copilot in a shared coding session, like if you're almost like a notebook where you can have simultaneous editors, but then the Copilot is there as an editor as well.
Going out there, pulling in things.
Yeah. Or if it was commenting on your code, that could be really useful, right? Like if it's highlighting stuff. I haven't actually used it, so I'm not sure if it does that, but like it's one thing to type in a function and then just like blindly let it copy and paste. But if you've typed in a function and it's looking back and saying, well, you know, frequently when people use, you know, sklearn, they always mix up these 2 parameters or something like that. That could be
that could be quite useful. The knowledge of many people in line with your production.
Exactly. How many thousands people went back and flipped those 2 parameters the other way around afterwards, you know?
Right.
I mean, like something similar. Like I'm already kind of like quote unquote AI assisted like code completion thing called Kite, and it basically like if you call a function, it already more or less pre-fills the like say for example, if you say train has split, it will already kind of give a hint of like what the main parameters are that you should, and also it kind of know the context of what you have done like a couple of lines before. So for example, if I'm calling my data frames, my custom data frame X and my custom data frame Y, it will know like this, that's what should be going to those parameters, and it also like learns from what you type most often. So it will actually like it will suggest the relevant APIs to what your more use, kind of like what you do more often first, sort of thing.
So
Nice.
personalized training, it's not just generic. It actually, I mean, kind of like Gmail adopts your way of speaking after a while for its auto suggest.
Yeah.
Yeah.
Interesting.
I picked up someone's phone once on a train, and when I opened it up, it was to try and send a message. Opened it up. This is a long time ago when we had clamshell phones.
Yeah.
And I opened it up and tried to send a message to the owner, and all of the shortcuts were these like crazy emoji like things. It was, you know, it was their way of writing basically.
That's hilarious.
But I think there's a interesting kind of equalizer that Copilot is going to apply, because all the big companies are going to be really nervous about adopting it because of the whole, like, you know, where did your source code get copied and pasted from? But all the startups don't really have a choice. So I think you're going to see a lot of smaller companies who are just like, well, we don't care. So in a way, it's kind of like in those racing games where they slow down the guy who's out front so that the other people can catch up.
Yeah. Well, that's what open source did generally, right? I mean, big enterprises had their code in-house. Right. And so more power to that democratization. Right?
Yeah. It's certainly, yeah, we engineers never thought we were going to be the first ones put out of work by software, but.
No, actually, I think that was often predicted. Some people actually said that very thing, is that
right.
Coding is the most ununique, uncreative exercise that there can be. And it kind of is.
A large percentage of it definitely is.
Yep. Yep.
But yeah, I mean, it's an arms race. As soon as you can automate that stuff, then presumably everyone will be competing on more
creative,
and harder to work on stuff.
Yeah. Before you know it, we're going to be talking about universal basic income. So before that, I'm going to take off. Great to talk to you guys.
Thanks a lot, folks.
Yep. Have a good week.
Cheerio.
Yeah.
Yep. Bye-bye.
Bye.